Thank you very much for inviting me. I believe it's the first time that I speak here in the context of a conference by a Solve IT, a company that is sort of also close to my heart. It has been founded about 20 years ago as a consequence of a joint publicly funded project. So very, very nice how this has developed over the years, and big congratulations to the company, how they have developed from these early days to wonderful products, and we're in business with always new ideas. Matthias Rarei's presentation is amazing. So why are we using software? And this is a diagram you have certainly seen before. So the efficiency in drug discovery is not good. Yeah, it's getting expensive, more and more expensive, and the output is not what we want to have. The projects get longer and longer, and we have to do everything we can to fight this trend. So this is until 2010, and it has just continued. And so our bet is that computational methods can stem the tide and get to a decent speed in projects. And yeah, so we will have a couple of ideas how to do this here. So the big challenge in drug discovery is that you have to balance a lot of endpoints. Yeah, so your compound here, compound we discovered in Darmstadt, which now has reached the market, tepotinib. So we had to satisfy all these endpoints in the same way. So it has to bind to the target, it has to be selective, but it has also to be stable and no side effects and all that. And this is a very, very tricky bit to get all these requirements under one roof into one molecule. And I'll set you a little bit the context what we are doing here. So the mission is to drive the compound design by computational techniques, so in order to be fast enough to get an output from project. And for me, where the industry is it's maybe no longer with the handcrafted molecules where a lot of attention is maybe even given in building the tools. This is a Mercedes-Benz Benz engine before the car was invented here. So very nice lab in a way. So then with Henry Ford, it got more into production faster, and my objective is certainly to make the drug discovery more of an engineering approach. So in the last picture, there are no people visible, but so there are people behind programming the robots, and I'm much convinced that all we are doing in computation techniques supports the human mind to take the right decisions and to increase productivity. I find it also interesting that one of the speakers here from the fragment-based approach said that then one chemist can run multiple projects. Yeah, so maybe this is the case also with computational tools to the help here. For us, we had big help from a project which was launched by our CEO, Stefan Oschmann, a while ago, where he said, so we must be more digital, we have to use modern methods. And so we gave sort of a bit here and said we have ideas, and digitally enhanced research and early development program came out of that, where we got a sizable amount of money where we could do novel things, hire people trying out novel things. And part of that, of the results of that, you will see. The funding is now over, so we are now hopefully harvesting the fruit of that. So we have heard in this two-day symposium many times how big the chemical space is, and in a way it's also wonderful for companies. So the chance that we discover novel things that our competitors have not discovered, even if we are working on the same target, is big. So that is good. So that is wonderful. But when you are faced with a decision, so you maybe have a hit, and you can imagine a lot of related molecules, which to make next. Yeah, do you do them all? And synthesis is still, once you have an assay, building an assay can be slow, but once you have an assay, synthesis is the slowest step. Yeah, and slow means also expensive. It needs hands, it needs time, needs people. So yeah, maybe do less synthesis, have less optimization cycles, and come up with the molecules faster and at less cost. So, and for that, our let's say engineering contribution is here to put machine learning and AI approaches to our help to find the decision on the next molecules to make, which then hopefully satisfy all the requirements. And this was from one project where with these methods, so we could satisfy, in this case, all but one property and move ahead. So then still the thinking chemist will have to work on Herc, but they have ideas how to get rid of Herc activity. And this is sort of a panel of assays we have used to build models. And over time, with the data we have, we come to good predictivity. So kappa is one of our measures. AUC could be another one. And the two green lines give an idea when the model is good, highly predictive, or very good. And with a number of them, we are in quite good ranges, certainly useful ranges. Most of our predictive models are in two-class models, so active or inactive, or low active, high intermediate, sometimes three-class models. And if you see like the fraction unbound, we also have continuous models. Our eventual goal is to have continuous models for everything, but it will just depend on the amount of data. And I will show you also one approach how to get more data by collaborating and collaborating with other industry partners here. And we also monitor over time how our models perform with new molecules that have been synthesized, and then regularly update these models as well. Still introducing the approach how the chemist would work with that, and you have seen this multiple times. So the chemist can draw or copy paste the molecule, and then he can choose here which models he wants to use. This is a in-house built interface, the Merck online computational chemistry analyzer. This is Mocha. We also have Cream. Cream is the back end for the generation of the models, and here he just ticks what models he wants to see, apply it, and then he gets the results here in sort of color traffic light color scheme, which does an immediate, here I'm already okay, but I have to work on these. So these little circles here give them also an indication of reliability. So we have an estimation how good the prediction is also here. And these are more the ADMET activities up there. But we also have a large kinase panel if you are in a kinase array where we have profiled 5,000 compounds on 300 kinases, build predictive models, and this is a full matrix. So these models are all pretty good. That give us an idea of selectivity here, that we can give an immediate indication to the chemist where he is. And then he will start to modify here the molecule, and we have not shown here the modified structures, and we'll try by his ideas to get all properties green. So this is still the traditional way the chemist thinks about new molecules, and then by machine learning AI supported methods, we judge whether the activities will be achieved. And this can be random forest models behind that, it's deep learning models, whatever we build large numbers of models and then select the best that we expose to be used by the chemists. We also learned that the chemists like yes, no, active, inactive predictions only mildly. They would rather want to know, yes, what property or what moiety in my molecule makes the effect or hinders me to achieve the effect. And in our long-standing collaboration with the Sepp Rochheit group and Günther Klamber, Christian Breuer at the University of Linz, AI people, with a strong dedication to chemistry, we have worked on methods which show us in the molecule which part of the molecule contribute to an activity. So this interpretability is quite important for us, and we also applied some in-house approaches here, the SHAP analysis, where again then we can map to a molecule which properties contributed to a certain decision whether a molecule is active and inactive. And once the chemist sees this, then he will immediately know to work on which aspects of the molecule and which side chains or rings or whatever an effort is needed. So that's quite popular here. And then here in more detail, the contributions we had here from the various parameters. All these models are built on fingerprints, so it's basically 2D descriptors, and I'll come to the 3D aspect a little bit later. I think eventually the molecules have to work in 3D, and there I would say methods still have to be developed. We are not quite there. When we generate these models, then we have a validation set and a test set, and here on a sample ADMET model you see we are doing well, so you think you are very happy, but all these are still then molecules we have been working on, which come from our chemistry. And then when you say, nah, let's see how does it do on new chemistry, and then we took just later data from the literature, and the performance of the models is suddenly very poor. This can have to do that the chemical space is so big that the models that we build only describe our chemical space well. It can also be that there are very, very strange molecules sometimes in public data, and that curation could rectify it a little bit. But still, I think it reflects that the models you can build as a company are built on a limited chemistry reflecting your history. In the case of Merck, 350 years history, but still it's limited. Yeah, and then when you want to go into total novel chemistry, maybe, and target also makes it necessary to go into novel chemistry, maybe all our models are not so good. And in order to approach this, we have been teaming up with a number of partners here in an European funded project called MELLODDY, Machine Learning Ledger Orchestration for Drug Discovery, where each company builds models on basically all the research data, and then by clever ways these models are combined into supermodels, which then hopefully increase the predictivity of the models for each partner and will allow for predictivity in chemical areas that were not accessible to the company before. So one outcome could be, even if your predictivity does not go up for your molecules dramatically, you will suddenly be able to predict also very different chemistry with good accuracy in that space. So 10 pharma companies coming together, a lot of data coming together in the model. So no molecule, no activity data ever leaves the company. Only the models, part of the models leaves the company and are combined. So security is a very big issue or aspect of this project as well. And there are dedicated partners looking only at that. We are just in the second year of 3 years, and the full one just is about to start these days or later. Fall we will know how good that is. But now to the large chemical spaces. So what I alluded to so far was more still the chemist working on his ideas, but can we exploit the molecules that are feasible, that can be rapidly made for rational drug design here. And from the beginning, of course, we have been using F-trees for a while, but when we saw the opportunities of this combinatorial chemistry approaches, we immediately said we want also basis on our in-house chemistry. And the good thing is we have an electronic lab notebook that we have developed together with Boehringer over many years now, and that continues. It's tailor-made to our needs. It is used for Merck worldwide, and 7 sites, more than 1,000 users, 1 million experiments in the 650,000 unique reactions. And we analyzed this volume of data to identify the chemistry we master, also the chemistry which may be unique to us, and to bring this in addition to publicly known reactions. And what we see here is a little bit the reaction statistics, what reactions are frequent. The thing with the reactions, it's complex. You have several hierarchies, depending how detailed you look at the reactions. And so the informatics behind that to actually make such an analysis about your reactions is quite tricky. It needs a lot of specialized know-how, how to work with it. Fortunately enough, there are some dedicated partners also to help with that. In our case, it took a very good postdoc and a dedicated scientist, so Tim Kniehans and Mireille Krier, who have been diving deep into that to make this a reality. And when we looked into this in our in-house reactions and public reactions, there is a big overlap. And when we look into this, when the additional reactions and the public reactions were thrown together, merging it into one big reaction space, and this big reaction space then was used to combine it with large spaces of building blocks using the Merck internal building blocks, E molecules, the Sigma Aldrich building blocks, and merging this all together with these reactions into our massive space. So our in-house space we generated. We were quite happy for a while, but it was the largest one. But now we learned GSK, the big company, they are now beyond us. And so about 10 to the power 4 reactants go in here, and 10 to the power 6 building blocks, and this combined multiple times leads to this 10 to the power 20 chemical space, which we then can use to find novel chemical matter, novel hit matter. And we also made sort of a little derivative where we just explore certain sites on individual molecules. That is very popular among the chemists. They come with the molecule and say, what can I do out of this molecule with a few or with available reactions for this and that active center, and with all the building blocks I can get my hands on. And this lookup space is also very widely used by the chemists and also directly used by the chemists, whereas the massive lookup with F-trees is more a thing that the computational chemists would do. So we have these two flavors, and so the full massive would be more like the universe and and miniMASSIV, so more focused one like a solar space or so. And the next steps are, that is also nicely was presented by the Janssen presentation a second ago, is then to, after the lookup, fast lookup, very nifty technology by Biosolve IT, very efficient, to screen the molecules we find for fitness before we present them to the chemist. So the chemist's time is the most valuable time here, of course, then doing the synthesis decisions. And so we use shape analysis, we use docking, we use ADMET predictive clustering, all aspects that have also been shown by the Janssen presentation in one way or another, to filter these down before we show them to the chemist, before the then expensive synthesis decisions are done. And also when you have to look at molecules, you don't want to look as a chemist at thousands of molecules, but if you share 20, 40, I think that is a good measure to discuss. And here's a little overview over a number of projects where we have applied the technology on various target classes, all sorts of target with different numbers of compounds analyzed. So the second column is here the result after the F3 searches. So the molecules which are presented as somewhat related to our query molecules. And then with synergies, we describe what additional filtering steps we applied here to get down to the numbers that then eventually are possible to be synthesized. And the outcome shows where we had a synthesis impact achieved, where better molecules could be derived from what we did here. And in most projects we found them, not always. We had the full impact that it propelled the project further and had a speed up on the project. But overall, it is a pipeline that reproducible and reliably gets result and makes a contribution to our projects. So the lessons learned from that, the ultra-large chemical spaces, or maybe we need other vocabulary now after ultra-large, there must be more. It's ever increasing, and we see this also, I think, from virtual screening approaches. Large spaces are good. Yeah, chemistry space is so big, and if you sample more of it, it is good. But then that is not, you need these engines, yeah, like the spaces, the search engines and all that. And I find it also very impressive how the development continues. I very much like Matthias Rarai's presentation here to see also how they address some aspects we see as a little bit of sometimes limitations. If you use F3s alone, sometimes the chemists feel, that is not similar enough to what I do, and then I will probably not synthesize it. So there are challenges, but to fine-tune this is certainly useful. And then the next step, of course, I mentioned is synthesis. Still, yeah, that is fast. No, that is not fast. That is expensive. That is slow. And the spaces like enamine wheel space, if you restrict your searches to those or others, they can guarantee fast synthesis, or you have dedicated in-house teams to do combinatorial chemistry that in-house fast. That is a good basis to start from. But with, I mean, for us, so when we're searching their spaces, 2 to 3 weeks, most compounds delivered, so that works very well. So the outsourcing, when you go to dedicated space, it's good when it goes to novel molecules. it can be slow as well. So getting the right chemistry into your mix certainly is important, also to have success and speed up here. So the commercial spaces are definitely very, very attractive here. And just to have a look at a number of a few case examples here. So the first step, usually look up in the large spaces. So this would be here our top cloud, the large spaces where we have some idea what we are looking for with MASSIV. So FG's behind that is used for the search, and then have a virtual screening filter where we search with properties, and the models for that have been derived by machine learning methods trained on our in-house data in combination with public data. And this allows then that a target profile is applied where exactly with the endpoints we have in mind for that molecule we can screen and have this screening step performed. Still, for now, this is limited to the molecules we have been measuring, where we have data plus the public data. So if the MELLODDY approach works out, then we will have, of course, hopefully much better models for this screening step, which is essential to go from the very large numbers to more handleable numbers. After that screening and usually also some chemist's eye, computation chemist's eye sorting, we may consider if it works to do FEP calculations. We have invested a lot to assess all our pipeline projects where we have structures with FEP calculations. We also published on that. I will show that in a second. And when it works well. Yeah, so it does not always work. So, and you do not always have explanations when it does not work. But when it works, it works, and you can predict your putative binding constant quite well. And so with these filtering steps, we then suggest the compound eventually for synthesis. For the FEP part, we had a look into our entire pipeline, which was target enabled here, and were able to get FEP validated targets, so where the models work, where the predictions are doing right. It can be that maybe you have the wrong kinase structure conformation as a starting point, and then it does not work. You can have other conformation and effects. So there are many possibilities why it does not work, but when it works, you can do good predictions, and we have quite large number of molecules synthesized here. So our experience is good, but it is a very expensive technology. So so here the cost can be limited, but still it's useful. And this is another example here in numbers. So after the first search here with F3s in a mean real space, about 1,000 molecules came out. Then there was a rocks shape approach, similar also to what Janssen showed, and then docking and GBSA applied here, machine learning model, and this boiled down then to a low number of molecules that were evaluated eventually with ideas. With FEP, where 8 ideas came out, which then were synthesized by Enamine very rapidly for low cost. Maybe one should not put it on the slide. Yeah, and the find
you
out.
have 10 minutes left.
Yes, that is perfect, and we were able to drive up the activity here considerably and have a trust in these rational approaches and in this pipeline of elements put together. So with that, I have mentioned there are still things to be done. Yeah, so a lot of things. So we are, with our experience, of course, happy that we have a good basis in terms of data and experience, and there is a lot more to come. So the biggest room in the world is a room for improvement. And for me, the area, and I did not touch much on that needs to be developed, is the 3D aspect. So a lot of what we are doing currently is on the 2D aspect. Of course, we are doing docking. We use, and I have not shown that a lot now, generative models. Most of them are based on 2D molecules, where initially synthesizability was an issue, but this is pretty much resolved. But I think the next step then is to put that together, really to build molecules, generative models based on feasible chemistry directly in 3D in the active site, taking protein flexibility into account. And this sounds a little bit like a dream, but you have seen, like recently, the protein folding problem has been solved basically. So Google Power has solved the protein folding problem, and maybe we will also solve in similar ways the drug design problem if we can really get the 3D aspect also tackled here. So this is for me the next necessary step to get drug design into truly a rational way into engineering. So we are working on that, and with that I thank all the people that have been working here hard to make that possible. And for us, we are a small company, yeah, bigger than others, but still we are a small company, so our resources are limited also in woman power, in manpower, and we could do a lot of this only because we had some extra funding, extra possibility to hire people, hire postdocs, and do collaborations also with Biosort IT, with other good companies here in the area. So if one wants to truly novel things, one also needs the funds. And we felt without hiring dedicated talent, it is difficult. Yeah? And that's also a risk when you hire postdocs and you can't retain them. Then sometimes what you have built up is not so easy also to maintain on the same level. But it will continue, as I said. So the area of 3D is an important one where still work has to be done. Biosort IT is also a strong tradition there. I think LexX built the success of the company initially, so strong know-how here. And so I'm looking forward to the next 10 years or more, and thank our collaborators.